So today we're looking at the topic of relative velocity, which, like we talked about yesterday, just compares the speed of two objects. So you might think that sitting at your desk right now, that you're sitting still, your velocity is 0. But in fact, we know that the Earth is hurtling around the sun at a speed of 100 kilometers per hour. In fact, we're all moving really fast right now relative to the sun, 100 kilometers per hour. Why don't we feel it? That's a great question.
It's like in a car, we don't really feel it.
In a car, sometimes you don't feel it. In a plane, when you're like flying really fast.
I feel like in a train.
In a space shuttle, because we all do that.
Or in a plane flying way above the sky, you don't always feel that you're moving. I mean, you feel it during the takeoff, but when you're actually going, you don't really feel it. And we'll see, especially with Einstein's theory of relativity, that there's a reason why we don't feel it. But we'll look at that at the end of the course. So let's pretend that we're driving down the freeway, going 100 kilometers an hour, when all of a sudden a white Escort hurtles by at 140 kilometers an hour. Type car. You don't perceive the Escort to be moving at 140, but when you look at them, it just looks like they're going at 40 kilometers an hour because they're going 40 kilometers an hour faster than you in the same direction. This used to happen to me when I was in elementary school. I'd be sitting on the school bus, and our school bus would slowly be going forward, and so would the bus beside us, but even slower, and it looked like that bus was like moving backwards. I always thought that was kind of cool. The relative velocity of any moving object depends on your point of view, or your frame of reference. So you see a car moving away at 40 kilometers an hour, but the other car actually sees you moving backwards at 40 kilometers an hour, because they're going way ahead of you. Now let's say we've got a zebra running away from a cheetah, and the zebra's going 50 and the cheetah's going 90. What velocity does the cheetah see relative to the zebra, and vice versa? So the zebra's going pretty slow. From the zebra's point of view, the cheetah is going 40 kilometers per hour forwards. The cheetah is racing ahead because the cheetah is going faster than the zebra. Now from the cheetah's point of view, he's passing the zebra, so it looks like the cheetah is moving backwards. From his perspective, the cheetah is going backwards at 40 kilometers an hour. So this is the zebra is moving 40 kilometers per hour backwards. And in physics, we can show the backwards by putting a negative sign. So in order to find the relative velocity, you can just subtract the two velocities. And this makes some problem solving a lot easier as well. Does that make sense? We're just comparing the velocities of two objects. So on the second page. I used to watch those videos of like animal attacks on YouTube in Africa, you know, like zebra dies by cheetah. So let's pretend that we're watching one of those YouTube videos. The zebra has a 90-meter head start. How long will it take for the cheetah to catch it and devour it?
Wait, are they going in a straight line, or?
Yeah, they're just running a straight line. So if you're an artist, you might want to draw a little picture. So what we can do is we can pretend that the zebra is standing still. The relative velocity of the cheetah can help us to solve this problem. The cheetah is going 40 kilometers per hour faster than the zebra. So we can pretend like the cheetah is just going 40 and the zebra still. The distance that they have to go is 90 meters. And we want to find out how much time is that going to take. So we just need the equation for speed. Speed is measured in kilometers per hour. Kilometers measures distance. Hours measures time, and per means divide. So velocity is distance over time. So now I just plug in my values. 40 equals 90 over t. And solve for t. So when I move the t to the other side, anytime you got a t in the denominator, you can multiply both sides by t. And that'll cancel off the t. And then you get t equals 90 over 40. But, yeah, that's right. I can't just plug in the numbers. I've got to make sure I've got the right units. This one is kilometers per hour. This one's meters. That's not good. They have to have the same standard units. So I need the speed to be in meters per second. So I'm going to take away, let's see, this 40 here. I need this one in meters per second, not kilometers per hour. Okay, so always look out for the units. So let's just do that on the side here. I'm going to take my 40 kilometers per hour, just means in 1 hour. 40 kilometers per hour means 40 kilometers in 1 hour. And now I need to multiply by a whole bunch of unit conversions in order to change it to meters per second. So let's see, I need to get rid of kilometers. Kilometers is on the top, so I need it on the bottom. And that can change to meters. I need to get rid of hours. Hours is on the bottom, so I need it on the top. I know how many minutes are in an hour, so I can do that. And then minutes is on the bottom, so I need minutes on the top, and I know how many seconds are in a minute. So I always set up my units first, so that I can see, okay, kilometers will cancel, hours will cancel, minutes will cancel, and that'll leave me with meters per second. And then I fill in the numbers. I know in 1 kilometer, there are 1,000 meters. I know in 1 hour, there's 60 minutes. And I know in 1 minute, 60 seconds. So then I just take the numbers and multiply everything that's on the top. So 40 times 1,000 divided by 60 divided by 60. Yay! That's 11.11 meters per second. I didn't keep the right number of sig figs because I never do the sig fig thing until the very, very, very last step. You want to keep as much information as you can until the very end. So now I'm going to put 11.11 here for the speed. So I'll take 90 divided by 11.111111. Keep as much information as possible so that your answer is as accurate as possible. And then I'll do the sig figs. So my question had 2 sig figs, so my answer can have 2 sig figs. Or I guess this has only 1 sig fig, so my answer will have 1 sig fig. 8 seconds. Oh boy. 8 seconds before that zebra is lunch. Poor zebra. Are there any questions? Okay, so we can also use this to solve some car problems. Okay, so we want to know relative to the second car, how fast is the first car going? If they're both going at 40 kilometers an hour. 0. 40 minus 40 is 0. Compared to the other car, it looks like the first car is standing still. So when you're driving on the highway at the same speed as someone else and you look right beside you, it actually kind of looks like they're just staying still. Now, compared to this car, how fast is this car going? It's going 20 kilometers per hour and it's making time. It's catching up. If the 20 kilometers per hour one is a zebra, he's soon going to be dead. And a harder one. Compared to this car, how fast does it look like this car is going? 60. It looks like it's going even faster. That's right. That's why when you're driving on the highway and you see other people coming straight at you, it looks like they're coming really fast. So technically what we can say is that one of these velocities is negative because it's going in the opposite direction. So then in order to find the relative velocity, you still can take away the two velocities. You do 40 minus negative 20. And that's how you get the 60. But it also is, it's common sense. It looks like it's coming really quickly. So last example. We've got two trains. One is 150 meters long. It's going at 13 meters per second, which is actually not as slow as it sounds. The other one's 100 meters long and it's going at 5 meters per second. And we want to know how long does it take for the long train to pass the short train. Now, because both trains are moving, this seems like a really hard problem. The longer train is first going to catch up, like this. And then it will pass. But we don't know how far both of them are going to move during that time. So how can we make this problem a little bit easier to solve? It's really hard to tell how far this train is going to move during the time that he's trying to pass. Yeah. Yeah, let's just pretend he's not moving. Pretend the short train is stationary. It's just standing still. Then this train is actually moving 6 meters per second faster than the other train. That's the relative velocity. So we can pretend like he only is going 6 meters per second, and then we just need to figure out how far does he need to go. How far does he need to go from here to here? Is it 150 meters? Yeah. Oh. This is what happens when you study math for too long. You get really bad at basic subtraction. That's right. 13 minus 5 is 8. Now I'm on YouTube and my friends are going to see me doing 13 minus 5 is 6. I'm sorry, friends. I'm not really as stupid as I look.
Don't judge.
Yes, that's right. I was just testing you guys. I just wanted to make sure that you were following along. So you want to go from here to here. So let's just take a look at from the start of the long train to the end of where the long train's front is going to be. So pretending that we're just the conductor at the front of the train, the conductor needs to go from here to here. How far is that? That's right, it's 150 for the length of the train. And it also needs to go 100 meters for the length of this small train. So the total distance that it needs to go is actually 250 meters. That's not exactly obvious unless you actually draw the picture step by step. So now, luckily, these are both meters per second and meters. Oh, happy day. We don't have to do any unit conversions. Oh, happy day. Velocity is distance over time. So how much time is it going to take? If you want, you can make the idiot box. Whee! Distance is on the top of the fraction, so distance will be on the top. V and t will be on the bottom. So if you want to find t, you just put your finger over t, cover it up, and d is on the top, v is on the bottom. So that's a nice little triangle way to manipulate the equation. Now we can plug in our variables. The distance is 250 meters. And the velocity is 8 meters per second. For a total of 31.25 seconds. And let's just change that to use the proper number of sig figs. How many sig figs do I have? 1, 2, 3. 1, 2, 3. 3 sig figs. How about the lengths of the trains? Yeah, well, exactly 3 sig figs. So 31.3 seconds. So the rest is just some practice for you guys. So what I'd like you to do is try out questions number 1, 2, and 9, and 11. And let's just do 1, 2, 3, and 5 from the last page. I'll write that on the board too. So you can do this on a separate piece of paper. Numbers 1, 2, 9, 11, and 1, 2, 3, 5. This you should finish in class. And then I've got some total review for everything that you need to know.